Okay, so the next thing we will start with is something called Dominators. So now once we have this very nice data structure called control flow graph, we can actually start doing some very interesting analysis and try to see what our program really looks like, what the program is sort of structured, what interesting things it has, how the control can flow, what all can it not do. So we can start reasoning on these things. And there are some very interesting data structures. Now all these algorithms will be taking the control flow graph as the input. So that will, now we don't even have to look at the program anymore because I have a very nice data structure that we can represent the program in. So, uh, let's define what are called dominators. Rather, I'll give a more intuitive definition. So I would say that a node D is said to be a dominator. Switch my pen. Yeah, okay. So a node D is said to dominate a node N if D and N are two basic blocks in the control flow graph, and any path that you take from the entry edge to the node N must pass through D. So there is no way to escape D before you reach N. If that is the case, then I say that D dominates the node N. Right? Is the definition clear? So I'm trying to list out all paths from the entry edge to the node D, and if there is entry edge to the node N, the entry basic block to the nth basic block. So we take all paths from entry to the basic block N, and if there is a node D that occurs on all such paths, all the above paths, then I would say that D dominates N. Are we sort of clear? At least you got the mental picture of what this is doing. Okay, so now for this control flow graph, can you tell me a dominator for node 5? Let me ask a question. Does 4 dominate 5?
No, maybe.
Why no?
Because path from 3 to 5 is not yet covered.
Exactly. So then, because there is a path like this also, so that does not include 4. So can you tell me one basic block which is a dominator for 5?
Node 2.
Node 2, excellent. Node 2 surely will execute. Will have to be there for every path. What about, can you tell me a node which dominates every other node in the basic block, in the control flow graph? Is there a node which is a dominator for every other node?
Node 1.
Node 1, exactly, the entry node. The entry node is a node which will surely dominate every other node, right? So this is the whole story about dominators. Now this dominator relationship is reflexive, antisymmetric, and transitive. So it's a partial order. Let me not get into the details because I'm sort of running out of time. I would like to cover some more material. And the dominators on a node N appear in a linear order by the domination relation. Right? So anyway, you can go back and try to prove these statements yourself. Just try to prove why is this a partial order and why does this statement, they are very easy proof. They are actually not difficult at all. Very simple graph theoretic proofs. Nothing. Let me just skip the proof. Now there is this definition called the immediate dominator. Now, if I take my dominators and any node, which is, like as it says that the dominator of a node is, so what does this statement even mean? Let us try to understand this statement. So the dominators of a node N appear in a linear order. So what it means is that if I take a node N and I collect the set of all dominators it has. Then, like if it has dominators A, B, C, D, and so on, then I can actually chain them up in some way where I can say A dominates, C dominates, B dominates, D dominates N. So there will be an exactly one way of putting this together in one chain. So there is going to be a like a one sequence in which you can line them up by this partial order, by the dominance partial order, right? So now for every node, right, I can find out what is the closest dominator to this. Like for example, I have dominator D, then I can always find out that this particular for node N, the D is the closest dominator. B is also a dominator, but to reach B, I have to first go through the dominator D, only then can I reach B. C is also dominator, but then I have to go through B, D, then only I can reach C. Right now, because I have things, so it's not that you do not have other nodes in between. So you can think of this as a path. So this linear order as a path, and then this A, B, C, D, and N appear on this path. Now, what is going to happen is, if you try to draw the mental picture, what could happen is that you could have other paths going from A to N, or the entry to N. But then these paths will, no matter which path you take, they will always go through these nodes. Right? This is the mental picture to put in mind. And now there is a node D which is closest to N among all its dominators. That particular node is referred to as the immediate dominator. I mean, the name says it all. Right? So, for example, in our, if I go back to our example, like for example, for node 5, 2 is also a dominator, 1 is also a dominator. But then which is the immediate dominator? 2 is the immediate dominator. Right? So this is the notion of immediate dominator. And then because things are lined up in that order, it is very easy to see that this dominance relationship, and more so because it's a partial order, you will see that this dominance relation actually falls into a tree. So you can actually arrange the nodes in a graph, in a control flow graph, in a manner that if I can put them as a tree, and these edges define the dominance relation. So essentially it says that D is the immediate dominator of H and A is the immediate dominator of D, right? And the set of dominator, how do you get the set of dominators of H? You just walk through the edges in the tree and you will get this set, which is nothing but the set A column. So it's now, if you represent your dominators in this tree, which is called the dominator tree, in that case, it is very easy to like find out the dominator of any node, right? All you need to do is you need to locate that particular node in the tree and walk up till you hit the entry node. And all the nodes you encounter in between are going to be dominators. And it is now very clear that these nodes are going to be in a linear order, because from any node to the root in a tree, there is exactly one path. There cannot be multiple paths. Right. So now once you have this dominator tree, this dominator tree is a very important data structure that very crisply captures the dominance information in a control flow graph. So now, if I want to construct the dominators of this particular control flow graph, can you tell me what would the tree look like? So I will have 1 is the entry node, so 1 will be there. So what will be the successor of 1 in the dominator tree, in the dominator tree? It will be 2. What will be the successors of 2 in the dominator tree? It will be 3 and 4. because 3 and 4 have their immediate dominators, which is 2. Where will 5 be? Whose child will 5 be?
Node 2.
Excellent, excellent. I was trying to trick you people, but you are too clever. So node 2, it has to be a child of node 2 because 2 is the immediate dominator of 5, right? Neither of 4 or 3 is the dominator of 5, right? So this becomes node 2. Then after for 6, this is 6. Then what about 7? Where should I place 7?
Node 4.
Exactly. This has to be node 4. And then 8 will be of this. So this is our dominator. Excellent. And then, as I said, I can collect the dominators very easily once I have this dominator. So how do I calculate these dominators? The algorithm to calculate these dominators is something called a fixed point computation. It involves something called fixed point computation. The idea is that for all nodes, you set the dominators to initially all the set of nodes in the control flow graph. And then what you do is you do this update. You say, now this is a fact, right? So if you have a dominator of a node n, that will surely contain itself, right? By definition. So n is a dominator of itself, right? Because you have to go through it before you can reach the entry level. And there is one fact, right? So if I have a node n and I have multiple predecessors of the node n, let's say P1, P2, right? And I have paths going from P1 to entry node and P2 to entry node. The path could be intersecting or be disjoint. So there can be multiple paths, of course. Now, what are going to be my dominators of n? Can you tell me that? So the dominators, so any node which is not a dominator of P1 and not a dominator of P2 can surely not be a dominator of n. That is very clear, right? Because if there is a node which is not a dominator of P1 but is a dominator of n, what does it mean? Right? It means that there is some node like this which is sitting up somewhere there, and it is not a dominator of P1. It means that there is a path where I can escape this particular thing and reach P1. That is why it is not a dominator of P1. If there is such a node exists that is not a dominator of P1, this node can surely not be a dominator of n, right? Because I can always show you this path, right? I can always construct this path which goes like this and then takes this edge, which does not include this node, and then that cannot be a dominator of n. That is very clear. So then, for something to be a dominator of n, it must be a dominator of P1 or it must be a dominator of P2. Now the question is that between P1 and P2, if there is a node that is a dominator of P1 but not a dominator of P2, in that case I can always construct a path through the other node, right? So let's say I have a node C1 and then I have a node C2. So let us say I have a node C1 which is a dominator of P1 but it is not a dominator of P2. So it means that there is a way of coming to all paths to P1 must follow C1, but paths to P2 need not follow C1. So this C1 cannot then be a dominator of n, because I can always show you the other path that does not follow C1 and comes to P2 and then take this edge and say that, see, I can tell you a path, I can give you a path which does not follow C1. So now the final thing to remember is that for something to be a dominator of my node n, it must be a dominator of all its predecessors, right? So this is exactly what this guy is doing. This guy is saying take an intersection of the dominators of all the predecessors, right? That selects all the nodes that are common to all the predecessors, and then this is a trivial dominator. So together is going to be the dominator of this node. Anybody has any problems with this reasoning? So I tried to give you a proof as to why this algorithm is even correct. So it's sort of a hand wavy proof. I did not really formally give the proof, but anybody has any ideas understanding this? So just to understand, when somebody asks you that something is a dominator, when you want to disprove if something is not a dominator, all you want to need to do is you need to construct a path which can reach that particular node without taking that node, right? For example, if I want to prove that C is not a dominator of N, all I need to do is I need to create a path from entry to the node N that does not go through C. That is all I need to do. And this argument is based on just that. Any questions?
Can you please give the example of C1, C2 again? It's a bit hard to visualize.
Okay, so let me just give that again. So first thing is that the necessary condition, right? So like, so if I have a node Pi, which is a predecessor of the node N, let me improve my handwriting, man. This I've been trying to do from my childhood, but never been able to. Okay, so let's say Pi is a predecessor of the node N. And I say that C is not a dominator of. So I'm just putting the relation as a. So I say that C is not not a dominator of Pi. Right? In that case, these two statements mean that C can not be a dominator of N. Are you convinced on this one first?
Yes.
Okay, good. So this our first job is done. So it means that any node, for any node to be a dominator, it must be a dominator of at least one of its parents. That is good. The second thing I'm saying is that if there are two parents of, or let's pick two parents of this node N, if Pi is a dominator of, so Pi and Pj are predecessors of node N, and I say that C is a dominator of Pi, but C is not a dominator of Pj. I'm saying this is the situation. Got it? So is it possible that C is a dominator of N?
No,
Why is that?
because it's not a dominator of Pj.
Yeah, so it's not a dominator of Pj. So what can happen is that I can construct so what does it mean that it is not a dominator of Pj? It means that there is a path that can miss C and still reach Pj. So if I can reach Pj without touching C, then I can just take the edge, because Pj is a predecessor of N. So I can just take the edge from Pj to N and construct a path from entry to N which does not contain C.
Sure, it's clear now. Thank you.
So yeah, so this also cannot be. So this says that it is not at least, it must be a dominator of all. It is not at least one. It must be a dominator of all its predecessors. Right? And this equation is just saying that. It is saying take the node N and take the intersection of the predecessors of the dominator sets of all the predecessors, because it must be dominator of all the predecessors. One problem is that this equation uses dominators on both sides, on the left hand side and the right hand side. And such equations are what are called fixed point equations. And they are generally not easy to even if they are linear, it's not easy to solve them, because you have the variables occurring on both ends, on the left hand side and the right hand side. So there is something called like fixed point theory, which actually talks about how to really go about solving such solutions, and when does a solution really exist for such systems of equations. And there are also algorithms to solve them and all. So I will not get into it, but the algorithms are very similar. It's very simple. I mean, they say that you start with a good initialization set. So in this case, a initialization set of n works. And what you keep on doing is you keep on doing this update. You keep on applying these equations to all the nodes again and again and again and again. If a fixed point exists, if a solution exists, in that case, sometime or the other, it will converge. That no matter you keep on running it, it will not, the solution will not change. And that is supposed to be the solution for this system. So that is how you solve it. I will not get into it because Professor Khetkar will probably talk a lot more about fixed point equations when he does data flow analysis. And then you will get to see how to really solve such equations. But at least you should understand that how to form this equation. The solving part probably you will get to know more. Okay, good. So I think we have understood it, and there were some very good questions. So I'm hoping we have. The next definition, and there are a lot of definitions because I'm sort of laying the foundation for the next few lectures. So the next important definition is something called a package. What is a package? So if you have your control flow graph and you have there is a node, there is an edge going from a source to a target. I mean, there's a reason I'm writing it like this. If there is an edge like this, then I say that this is a package if my target dominates my source. That is, from the entry, there is no way to come to my source without going through the target. If that happens, then I call this a package. There is nothing to understand here. This is a definition. So there is no reasoning here. So this is just the definition of a package. This says what I classify as a package. It simply says any node where the dominance relation occurs in the opposite direction of the direction in which the node is flowing, I will call it a package. Are we good? Any questions with package? Okay, so this is just a plain definition. There is nothing to it. So can you tell me that what is a package here? Or let me just go back to the dominance tree that is. So yeah, so now we have the dominance tree also, and we have the control flow graph also. Can you identify the packages for me?
Node 5 to node 2. The edge from 5 to 2.
5. So why is the edge from 5 to 2 a package? Because the edge is flowing from 5 to 2, but the dominance relation is flowing from 2 to 5. Right? So that's the package. And the same goes for the edge 6 to 2 also. Right? Because 6 to 2, the dominance relation goes in this direction, while the edge goes in the other direction. Edge goes from 6 to 2, while the dominance relation goes from 2 to 6. Right? That is why these are my two packages. So I have two packages in this case. I have a package which goes from 5 to 2 and another package which goes from 6 to 2. Excellent. Thanks for the answer.